Welcome to Hartman Math. This is lesson 3.2, Logarithmic Functions and their Graphs. So we're going to take a look at a log function. Our x, we call that our argument, what we're taking the log of, has to be positive. And then just like in our last lesson when we were talking about exponential functions, a, which is the base of the log this time, has to be positive. And that base cannot be 1. So we say that y equals log base a of x if and only if x equals a to the power of y. So they're essentially equivalent expressions, one written in log form, one written in exponential form. So it turns out that where the log comes from is it's the inverse of the exponential function y equals a to the power of x. And so the way that we read this is f of x equals log base a of x. So we say the word base, then we say the base, we say of the argument x. So first thing we're going to look at is evaluating logarithms, such as log base 3 of 81. And there's this connection to exponents. 3 is our base, 81 is the argument. So essentially, you can think of a log as an exponent. So we're really saying 3 to what power equals 81. And some of these we can do mentally. So 3 to the 4th power is 81. Our answer is 4, like this. This is not the answer. It's kind of evidence and the way we work through it. But the answer is 4. The answer is a number. Now, if it's a little bit more complicated where we might not know, such as log base 27 of 9, there's some other things that we could do. Because if we're saying 27 to what power is 9, maybe you don't know, and that's fine. So here's a way we can go around it, and then we'll talk about how we might be able to still do this mentally. But we can turn this into an equation, and then we can rewrite this equation from log form into exponential form like we saw in the last slide. And the way we do that is we move the base. 27 is the base, so it's going to move to the other side. It's now going to become the base of the exponent. That bumps up the k to be the exponent. We're left with 9 on the left side. No more log anymore because we're writing it out of log form into exponential form. And then what we want to do is come up with a common base for both sides. 9 and 27 are both powers of 3. So this is 3 to the 2nd, and that is 3 to the 3rd. So we'll rewrite them as powers of 3. Keep in mind over here that 3 to the 3rd raised to the k. When we raise a power to a power, we multiply the exponents, which is why this is 3 times k. Now the bases are the same. We saw this before. This is the 1-to-1 property. So 2 equals 3k. We can solve from there. And we would get 2/3 before we get to the checkpoint. How could we do this mentally? Well, again, if we kind of knew that we needed to get this to, hey, having a common base of 3, what would I do to 27 in terms of exponents to get it to be 3? Well, I could take the cube root. That means 1/3 power. Now that it's 3, what do I do to that to get to 9? Raise it to the 2nd power. 1/3 power, 2nd power, multiply them together, and we get 2/3. So either way you want to go about it is fine. All right, go ahead and pause here, work through the checkpoint. Now, what they're asking these in a slightly different fashion, but we're basically saying, hey, if I'm going to do f of 125, I'm talking about log base 5 of 125, and now I just evaluate it. So pause here, get your answers, and then resume. All right, first one, 5 to what power is 125? That one's pretty quick. The 3rd power. Log base pi of 1. So pi to what power is 1? That would be 0. That's the 0 exponent property. The decimal's kind of tricky here. I would probably maybe want to think of this as 1/2. So 4 to what power is 1/2? Well, if we square root the 4, that would be the 1/2 power. and then it's 2, and then to turn it into 1/2, we got to flip it, and that's a negative. So, however you worked it out, it's negative 1/2 on that one. All right, so some common or some important bases for logarithms. We're going to start with base 10. Base 10 is called the common logarithm. On a calculator, you're going to see it's just the log button. So if you see log written with no base shown, we're talking about base 10, and that's the common logarithm. One place where you've probably heard of common logarithms, although you may not have known about it, being that we live in the state of California, one of our geological phenomenon is earthquakes. When an earthquake happens, you're going to hear it reported, and it's reported with a number. So that number is on the Richter scale. So if they say there was an earthquake that happened around Susanville, and it was a 4.5 magnitude. That's 4.5 on the Richter scale. That's a logarithmic scale, and it's a logarithmic scale of base 10. So we're talking about a 4.5 compared to a 5.5. The 5.5, since we're talking about base 10, is 10 times more energy released, damage that could be expected, than a 4.5. If we have a 6.5, that's 10 times more powerful than a 5.5. So the question is, how much more powerful is a 6.5 than a 4.5? 2 on base 10 is 10 squared. That's 100 times more energy. Example number 2, evaluating common logs on a calculator, pretty easy. If it just says log 75, that's all you have to do. Press the log button, 75 equals, we're going to round to 3 decimal places, you should get about 1.875. All right, some properties of logarithms. Log base A of 1 will always be 0 because of the 0 exponent property. Log base A of itself is always going to be 1. Because A to what power is A? That would be 1. So this one we want to look at, probably put a little time into thinking about, as it's not as obvious as the others. Log base A of A to the power of x will be x. Log base A and A to the power of, or inverses, kind of cancel each other out. The answer is the exponent. And then the reverse of that, A to the power of log base A of x, same thing. A and log base A cancel each other out. We're left with the answer being the argument there. And then a one-to-one property, very similar to what we saw for exponential functions. Log base A of x equals log base A of y. As long as the bases are the same, that guarantees that x has to equal y. So let's see if we can simplify, for example, number 3, using some of these properties. Log base 9 of 1. Even if you don't remember the property, which means 0, you can still ask that question, 9 to what power is 1? And we know that's 0. Log base root 11 of root 11. Okay, well, these match, so it's got to be 1. And then our inverse property, 8 to the power of, log base 8 of, they cancel each other out. We're left with 30. 30 is the answer. Example number 4, let's use a one-to-one property to solve this. So notice it has log base 3 of, if we think of this in terms of our properties, x equals log base 3 of y. So the only way this can be true is if that equals that, and that's how we set up our next step of the equation. Now let's solve for x. Square root both sides. Don't forget it's plus or minus. So x equals plus or minus 5. Now, remember from before that there's an issue with the domain of the log function. The domain of the log function, the x, the argument has to be positive. Now in this case though, we're talking about this has to be positive. This has to be positive. So if we substitute in 5, we get 5 squared plus 4 is 29. That's positive, no problem. If we substitute in negative 5 squared is also 25 plus 4 is 29. That's positive, no issue. Both of them work. Just an idea that you're going to want to check anytime that we're solving a log equation because of the domain issue. They both work, box your answer. All right, let's take a look at graphing. So if we remember, we graphed this one in the previous lesson, 2 to the power of x. We had a point at 0, 1. We had a point at 1, 2. We got close to the x-axis, which was the asymptote. And these were all the features or characteristics of the graph: its domain, its range, its y-intercept, and its asymptote. Well, the log base 2 of x, notice the bases are the same, is the inverse. So we can use the idea of what we know about inverses to help get this, which is we can reflect our graph across the line y equals x, or the way we've created inverse is to switch x and y, so we can switch coordinates. This is 0, 1, so on the inverse it's got to be 1, 0. This is 1, 2, we can go to 2, 1. The graph's going to look like this. Notice that they're reflections of each other in the line y equals x. So what's the domain of this? Well, notice that all of our points are to the right of 0. Notice how this matches that. X's here match the y's over here. Remember, we switch x and y for inverse. What's the range? Down forever, up forever. All real numbers. Matches there. X-intercept, 1, 0. Asymptote. We're getting close to the y-axis. That's the equation x equals 0. Now, for the future, if we want to graph a log function, we don't need to have the exponential function to get us started. We can just go based off of this idea, where we're talking about log base a of x. We've got a point at 1, 0, and then this point is going to be base, 1. Here our base is 2, so it's 2, 1. If that was log base 5 of x, we'd do 5, 1. So let's take a look at h of x. We're going to graph the base graph first, and the base graph stops at the x. So that would be log base 3 of x as our parent function here. So the two key points, 1, 0 and 3, 1, because we're talking about base 3. I'm going to graph that dotted because it's just my base graph, not done yet. Now I need to shift my graph. This says we're going to shift 1 to the right. So both of my points are going to go 1 to the right, but also my asymptote, which was here, it's going to go 1 to the right, and I'm going to redraw that asymptote. The domain, everything is now to the right of 1. The range still down and up forever. The x-intercept is 2, 0. The asymptote is x equals 1. All right, checkpoint, see if you can graph k of x, get the domain, range, x-intercept, and asymptote. Pause the video here as you work through. Hit play when you're ready. All right, so our base graph stops at the x, log base 2 of x. We've seen that one before. The plus 3, not in parentheses. So that's after the log function, which means we're going to shift up 3. There we go there. So our domain, everything's to the right of 0. The range, down and up forever. X-intercept is going to be tricky. What are we guessing here? I think we want to think of this in terms of an equation. So we know that for the x-intercept, that the y-coordinate, k of x, that would be 0. So if we kind of think about maybe solving this equation for x, If it's 0 equals, we could then subtract 3 both sides. So if we start here, 0 equals log base 2 of x plus 3. Subtract 3 both sides. Now let's rewrite it out of log form into exponential form. We're going to move the base. So the 2 moves to the other side. It's the base, and that's going to bump up the negative 3 as the exponent. What is 2 to the negative third power? It's going to be our x-intercept. So it's 1/8, 0. Our asymptote, x equals 0. So our next important base is base e. This is going to be the natural logarithmic function. So we're talking about log base e of x. Remember e from our previous lesson. E is that natural base, about 2.718, something like that. Well, the way that we would write that typically is ln of x. It's not a capital I, it's a lowercase l, ln of x. ln of x. And the reason that it's ln instead of natural log is think back to possibly one of the foreign language that you're taking, if it's Spanish or if it's French, and ask yourself, in that language, where does the adjective occur in relation to the noun? Because in English, the adjective occurs first. But in French or Spanish, let's think back to French, because that's where this comes from, is the noun comes first, logarithm, and then the describing word, natural. That's why it's in that order. That's why it's ln. So f of x equals ln, or the natural log of x, and x has to be greater than 0. And you have that button on your calculator, the ln button. So if we want to evaluate that, for example, number 8, the natural log of the square root of 111, just press the ln button, type in root 111, and you should get about 2.355. So we'll go real quickly through these. So those properties we were talking about before, they apply to natural logs as well. The natural log of 1 is 0, again because of the 0 exponent property. The natural log of e, remember natural log is log base e. So we're talking about log base e of e. That's got to be 1. The natural log of e to a power is the power because natural log and e are inverses. And then the 1-to-1 property, the natural log of x is equal to the natural log of y. That means that x would have to equal y. So let's see if we can simplify or evaluate using those properties of natural logarithms. Again, now we're talking about an inverse property. Natural log, e to the power, cancel each other out. The answer is the exponent, 1/2. Same thing here, e to the power of, natural log of 8, e, natural log, cancel out. We get 8. What's the natural log of e? It's 1 over 6, 1/6, property 2. Example number 10, find the domain of the function. So we got h of x equals log base 7 of our expression here. Well, again, the argument, and here's our argument, for a log function has to be positive. We had said before that the x would have to be greater than 0. Well, in this case, this has to be greater than 0. That's our setup. And now it just becomes a nonlinear inequality. We covered that back in chapter 2. You can factor that. You factor it all the way. You get x times x minus 2 squared is greater than 0. We could do that algebraic, or we could do it graphically, which would mean Here's our graph. Put our x-intercepts. 0 and 2. It's third degree, so it's going to start low and end high. It's going to cross here, and at 2, because of the multiplicity, it's going to bounce. Now, we're looking for where is our graph above the x-axis. Here and here. So our algebraic solution for our domain would then end up being from 0 to 2, the union, 2 to infinity. There's the domain of the function. All right, let's finish with a checkpoint. Find the domain of the r of x function. Pause here till you're ready. All right, we've got a similar situation. We're talking about a logarithm. Doesn't matter if it's natural log or whatever. The argument has to be positive. We're going to say this is greater than 0. So when we say that's greater than 0, we've got a couple options here. We can factor the denominator. We get all the critical numbers. 1/2, -1, 3. So we mark all those out. We can test the intervals. Substitute in a -2. It's not true. Substitute in 0. We're going to get -1 divided by -3. That's 1/3. Is that greater than 0? True. If we substitute in 2, it's not true. If we substitute in 4, it's true. So we're true here. We're true here. So from -1 to 1/2, and then from 3 forever to infinity, there's our domain. That's it for today. I'll see you next time.